Hi, everybody. Today we're doing section 4.2, and that has to do with uh, calculus with two variables, or on functions of two variables, I should say. In other words, in the last section, we talked about just some of the how to deal with a function of more than one variable, a bunch of functions of two variables. And of course, like I say, a function could be two variables, three variables, 27 variables, but we're limiting things to two variables now. And uh, but we didn't do any calculus in the last section. We just got the idea of what a function of two variables is all about. Now in 4.2, we're actually going to start to do some calculus on these functions. So first, I have to say that everything we learned in the beginning in just regular calculus with y equals f of x, that's that's everything. In other words, the beginning calculus is everything. Um, so multivariable, this, that, the other thing, that's all just taking the calculus and applying it in different arenas. But you really know everything you need to know. We just have to apply it and adapt it a little bit in different situations. So you guys are already experts, even though you don't realize it. So let's look at this. I'm going to share my screen. So I want to just start with just a little talk about well, what do people always talk about? People always talk about the weather. So I want to really start by talking about the weather. So I'm going to share my screen. Now, this is called a wind chill factor or wind chill chart. You may not have heard of this. Growing up in San Diego, this is not, that big of an issue, but I grew up in New York. It's a very big issue there. So here's the deal. Let's say it's a cold day. It feels colder if it's also windy. You see what I'm saying? There means there's, and that's what wind chill means, meaning that there there's the actual temperature, and then there's how you feel. So if you look over here, for example, let's see, let's look at let me get a brush. So if you look here at so what does that mean? If the actual temperature is 25 degrees and the wind is going at 30 miles an hour, even though the actual temperature is 25, it's going to feel like it's 8 degrees. Let's actually look at this whole column. Let's see. How do I change the color? Oh, let's make it. Okay, so let's see if that works. Oh boy, I want a better color. I want my money back here. Let's see. How do I get this color? On the, so here, let's look at this column right here. Oops. We back up a little bit. Let's do that again. Let's do that again. So I'm just looking at the, oh, I'm doing the same thing. And then every time I okay, that's what happens when you're on live TV. Okay, so if we go down this column, it's 25 degrees and it's calm, meaning there's no wind. It's going to feel like 25 degrees. If it's 25 degrees and there's a 5 mile per hour wind, it's going to feel like 19 degrees. If there's a 10 mile per hour wind, it's going to feel like 15 degrees. If there's a 15 mile per hour wind, it's going to feel like 13 degrees. If there's a 20 mile per hour wind, it's going to feel like 11 degrees, and so on and so forth. If it's 25 degrees, which is pretty cold, by the way, 25, that's actually below the freezing point of water, then it's going to feel, if there's a 60 mile an hour wind, which is quite windy, it's going to feel like it's going to feel like 3 degrees. So that's called the wind factor. In other words, the wind actually makes you feel colder on a cold day. And that's, again, um, a lot of my students who are in San Diego never even heard of this concept because it hardly applies here at all. But in New York, it's just part of your life. There's also so but if you notice what I'm doing here, the how you feel, the how you feel is a function of two variables. It's a function of the temperature and it's a function of the wind velocity. So if it's 15 degrees temperature and it's 15 miles an hour wind, it's going to feel like 0 degrees. If it's 35 temperature and it's 40 um, and it's 40 mile an hour wind, it's going to feel like 20 degrees. So it's a function of two variables. But what I'm really interested in is just this column that we looked at over here. What I'm doing here is that I'm isolating the temperature and I'm just looking at how everything changes as the wind changes. And this idea of sort of I was going to say freezing one variable with no pun intended. I'm freezing the temperature variable, and I'm just looking at how the chart changes as the wind velocity changes. That's what we call in math a partial derivative, meaning that I have I have I have two variables here, but I'm sort of like freezing one variable and just seeing what happens as the other variable varies. And that is the idea. So now I'm gonna show you some x's and y's and stuff like that, and show you how to figure this stuff out. So let's go to our I'm gonna go to our other camera. Okay, so here we go. Let's say we have a function. Let's say we have a function f of x comma y equals x squared minus 4xy. I'm sorry, my finger's in the way, but I have to hold the plus 4y squared. So what I want to do is I want to freeze y, and I want to treat x as the variable. So as far as x is concerned, y is just a constant, and we're gonna take the derivative in that manner. Now, what you do here, the notation for that, you write it this way. You write fx, f sub x of x comma y. Now that means you're looking at the function f of x y, x comma y, which is equal to this guy here. You're going to take the derivative, treating x as though it's a variable and treating y as though it's a constant, just like we had in that sort of intro. That we were looking at. Remember, we were sort of freezing the temperature variable and just looking at the wind changing wind velocities. Anyway, so 2x, the derivative of 2x, well, is just 2. Everyone knows that. Um, Now, the derivative of minus 4xy, remember, the 4y is considered a constant. So it's just minus 4y because it's the constant 4y times the variable x, and the derivative of that is just the constant. And now this is the greatest part. The derivative of 4y squared is actually 0 because 4y squared is just a big constant. Even though y is a variable in its own right, but as far as x is concerned, y is not moving. We're looking at the movement of x when y is still and y is constant. So that's it. We're done. This is the answer. Now, suppose I want to do the opposite. I want to treat x like the constant and treat y like the variable. Well, then the way I write it, I write f sub y of x comma y. So now let's go back all the way up to the top. Now, x squared now is considered a constant because we're only talking about y changing, but we're talking about x being stuck in one position. So since it's a constant, the derivative is 0. Here, again, the x is a constant, so it's minus 4x times the variable y. So the derivative is just minus 4x. And over here, we have y without any x, and that's the variable. So that's going to be plus 8y. because that's the derivative of 4y squared. And that is the answer. And this is called a partial derivative. Partial derivative. By the way, I assume the reason it's called partial is because this is a function of two variables, but we're only taking the derivative with respect to one variable, or at least one variable at a time. So each of these is called partial derivatives. Let's do another example. F of x comma y equals the ln of xy plus xy squared. Okay, now I'm going to simplify this a little bit. I'm going to get rid of this parentheses. So I'm going to have plus x squared y squared. And that's actually going to help us. And the ln xy, I'm going to simplify this in a way also. I'm going to use from algebra, the law of logarithms tells me that this is equal to the ln of x plus the ln of y. And now that we've done these few little algebraic um, manipulations or simplifications, or whatever you want to call it, we're going to take the derivative. So first we're going to take the partial with respect to x, and we write it like this: f sub x of x comma y. Now, ln x is a variable. The derivative of ln is 1 over x. Y is just a constant, and ln of y is another constant. So the derivative just disappears. It just becomes 0. And I'm going to write plus 0. Now, here again, the y is a constant. X is the variable. So it's just going to be 2. I'm going to put the y squared in front because it's a constant. 2y squared x. Why did I do that? Because the y squared I just put over here. The derivative of x squared is just 2x and pound. So that's my answer, 1 over x plus 2y squared x. Now if we find to get the partial with respect to y, well, again, we're going to focus over here. This is what we're focusing right there. So ln x is just a constant because y is considered like a constant. Ln y, that's going to be 1 over y. And here I'm going to do the exact same thing I did before. It's going to be 2 times x squared times y. Because why is that? Because the derivative of y squared is 2y. So that's the 2 and that's the y. And the x squared I'm just leaving in the middle. I just like writing it that way. And that is my answer. And that is quite remarkable. I want to do another example here. And here we go. So f of x comma y is equal to x squared plus y cubed raised to the 5th power. Okay, now let's start with f sub x. Now, I wanted to introduce something. Now that we get a little, you know how in regular calculus that we've been doing till now, which we did in the first several chapters, there were two ways of writing a derivative. We could write y prime, or we could write dy dx. So what I'm showing you now, this f sub x and f sub y, that's kind of like the y prime notation. There's another notation which is similar to the dy dx notation, but what you do is instead of writing dy dx, you write del y. Now, in this case, it's not y, but it's del f, del x. Meaning f is the function, and we're taking the derivative of the function. F of x comma y is the function. We're taking the derivative of that with respect to x. So this and that is just two ways of writing the same thing. This is f sub x. These are the same thing. I just wanted to show you a second notation. But now let's get to the important part, which is the mathematics. So first of all, we're going to use chain rule. So it's going to be 5 times this sucker to the 4th power times the inner derivative. Now the inner derivative, x is the variable here. So the derivative of x squared is 2x. Y is a constant. The derivative of a constant is 0. So that's it, pow, done. Now, of course, you could simplify this. You could multiply the 5 times 2 and get a 10. But right now, I just want to show you the calculus part of it. Now, f sub y, and again, another way of writing it is del f del y. Well, interestingly enough, the outer derivative will be the same thing. It's going to be 5 times x squared plus y cubed. That doesn't change. But the inner derivative, well, x squared is just a constant, so the derivative of x squared just disappears. Y cubed is the variable, and that's just 3y squared. And there you go. By the way, here I wrote parentheses, here I did not write parentheses. It wasn't truly necessary to write the parentheses here. It's just when I started this, we didn't know that the y cubed was going to disappear. Anyways, these are examples of how you do partial derivatives. Now I want to look at this top function here, f of xy equals x squared minus 4xy plus 4y squared. And I want to graph that. So let me share my screen with you. Now I'm graphing that I'm not graphing it in decimals like I usually do. I'm going to graph it in GeoGebra because this is a three-dimensional function. So I'm going to my 3D calculator. It's right here. And okay, I'm just going to use the variable z. I don't think it matters. Actually, I never tried. I want to see how it works with GeoGebra if I type in f of x comma y. X equals the x squared plus minus 4xy and minus 4xy. Okay. Oh, interesting. So this is kind of what it looks like. And I want to look at the point. Interesting. Oh, interesting. Now, why isn't it usually if it okay. So this is notice it this way, it's kind of like a parabola. If you look at it from this direction, it's kind of like a probably even if I do it really right, I could make it like totally I could if I could line this up right, I could looks like it could be a parabola. Okay. Um so so let's I want to now go back to some calculus. So I'm going to go back to I'm going to stop sharing the screen. I'm going to go back to our camera there. And what I want to look at for this problem here, I want to evaluate the derivative at the point 0, comma 0. And I also want to evaluate, and then I'm going to evaluate at a different point. So f sub x of 0, comma 0, so that's equal to 2 times 0 minus 4 times 0, which is just 0. F sub y of 0, comma 0 is equal to negative 4 times 0 plus 8 times 0, which again is just 0. Now, what that tells me is that at the point 0, comma 0, this function is kind of like flat, or it means like a minimum. Just like in or the tangent, so to speak, is just sort of a flat horizontal, and you really can see that. You can see that from the picture here. Let's go back to the picture. It, uh, it's kind of like the bottom of a parabola, so so that indeed works. Okay, let's go. Let me just unshare my screen. I want to look at another point. Let's look at the point 1, comma 1. So f sub x of 1, comma 1 is equal to 2 times 1 minus 4 times 1, which is equal to negative 2. F sub y of x of 1, comma 1, I'm sorry, is equal to negative 4 times 1 plus 8 times 1, which is equal to 4. So notice that f sub x is a negative number and f sub y is a positive number. And what this tells us, this is very significant. What this tells us, excuse me, is that above the point 1, comma 1, the surface decreases if you move to a more positive x values, and it increases if you move to more positive y values. And that's again amazing things you could see about a function. Okay, so I want to do one more example, one more nice little example, and here we go. Here's our example. This is a new one here. I want to find so f of x comma y is equal to, now we have a big fraction here, e to the x plus y over y cubed plus y plus y ln y. So it's y times ln y. So I want to find, I want to find del f del x. So that means I'm going to treat x as though it's a variable and treat y like it's a constant. Okay, well, here, so basically the y cubed plus y is just a constant, and it's going to just come along for the ride. Now, if a constant is added on, and the derivative just disappears to 0. But if a constant is being multiplied, then the constant just sticks around, so to speak. So I'm looking now at e to the x plus y. Well, the derivative of e to the x plus y is e to the x plus y times the inner derivative, which is just 1. So the derivative of this guy is just going to be e to the x plus y, I guess technically times 1, but like who cares, over this constant y cubed plus y. And this part, y ln y, that just disappears. And this is the answer. So again, that's how it works as far as x is concerned. And that's kind of interesting that the derivative winds up being the exact same thing as the original, well, almost the exact same thing as the original function. Because this part of it disappeared. But the derivative of this big fraction winds up being the same big fraction. Now let's do del f del y. That's gonna be a lot more work. Because not as much is going to disappear. So I'm going to stay in purple, and I'm going to okay, del f del y. So again, now this is going to be I have e to the x plus y. So the top part is a function of y. The bottom part is a function of y. So I'm going to have to use quotient rule. Here we have y is a function of y and ln y is a function of y. So I'm going to have to use product rule. Let's do it. So for quotient rule, we have the derivative of the top, which is still going to be just e to the x plus y, times the bottom, y cubed plus y, minus the top, e to the x plus y, times the derivative of the bottom, which is 3y squared plus 1. And all that is over the bottom cubed. Y cubed, squared, I mean, plus y squared. And now for this part, I'm going to use, so essentially we use quotient, for this part we use quotient rule. Now for this part over here, we're going to use product rule. So let's do that. So that's going to be the derivative of y is just 1. So this is going to be 1 times ln y plus y times the derivative of y, which is 1 over y, which simplifies, of course, to just 1. This is really, that last thing is really a plus 1. So the answer is going to be, now, by the way, I wanted to just talk about simplifying. It's good to simplify, but this is the rules. If I don't ask you if on a test I do not ask you to simplify, and you get the correct answer and you do not simplify, I will still give you full credit. If you attempt to simplify and in the simplification you get it wrong, even though your original derivative was correct, you like made it wrong afterwards, after the fact, you lose points for that. So it's pretty, therefore, it's up to you. It's up to you. Sometimes it's, as we've seen, sometimes it's, helpful to simplify, but sometimes you could just leave well enough alone. Anyway, that's our final answer. It's very beautiful. I'm going to do one last example for this video. This is actually going to be a part 1. I am going to make a part 2, but I want to do one last example because I know what you guys, a lot of you are thinking. You're all thinking, "Oh wow, this is so much fun. Have with a function of 2 variables. Oh, so much fun. Oh, it's such a shame we don't get to do more than 2 variables." Well, it's the shame is over and the fun begins. So I'm going to give you a function now of not just 2, not just 3, but 4 variables. Okay, so here's our example. We're gonna look at f of x comma y comma z comma w. That's 4 variables, and that's equal to 35 x squared w minus 1 over z plus y z squared. Now this is pretty horrendous, and I want you to find f sub z. Well, 35x squared w is just a constant, so it's going to disappear. The derivative of negative 1 over z is positive 1 over z squared. The derivative of y times z squared, well, y is a constant, so I'm just all I have to worry about is the derivative of z squared, which we know is 2z. So it's going to be 2yz, and that's it. We are done. Now I want to show you. That's the last example. I just want to show you the official definitions of partial derivatives. And let's actually, you know what? Yeah, I just want to show you just how the textbook officially writes it, and then we're going to sign off. So let me let's see. I need to share my screen with you. And here we go. So partial derivatives. The partial derivative of f with respect to x is the derivative of the function xy. we think of x as the only variable, and we let y act as a constant. And with respect to y, it's the same thing, but other way around. And again, the word with the respect to is very, very important, because that tells you which is the constant, which is the variable. And I like the way he says it, which is the variable. Now, geometrically, a partial derivative with respect to x gives the slope of the curve as you travel along a cross section, and a curve on a surface parallel to the x-axis. The I mean, specifically a curve which is on the surface parallel to the x-axis. The partial derivative with respect to y gives the slope of the cross section parallel to the y-axis. That's pretty awesome. And the notation is, like we said before, that the partial derivative of y equals f of x. Either write f sub x of xy. Sometimes you write zx because I think this is of y equals f of x. Or sometimes you write f sub x. I think this line right there, I believe that to be a mistake. That should be y. That should be f of x comma y. That should be z equals f of x comma y. But either way, the other way to write is del f del x, or del z del x. And so del x of f of x comma y is del f del x. These are all just a whole bunch of ways of saying the same thing, and they're just different notations. I kind of wanted you to see all of them. And that, my friend, is that. So we are going to make a part 2 of this topic. Meanwhile, I just wanted to actually let me come and see you all again. Let me see how handsome I am. So we're going to make a part 2 of this video. Meanwhile, I am going to say bye. Bye, everybody. It's been loads of fun. Bye bye.